we find how long ago was the Big Bang. Okay? This is a relatively recent discovery. The discovery of the Big Bang by theoretical physicists was at the end of the 1940s, but experimentally it came in 1920s from one side, and another independent, different kinds of observations came in the 1960s. So it's rather recent that people realize that the universe as a whole is dynamic, it's moving. And then it must have started this motion at a certain time back. Okay? And now let me write this age of the universe. Age of the universe, so I mean time since the Big Bang is 10 to the 10 years. To the 10 years, well, let me express that in our basic unit, the second. 1 year is 3 times 10 to the 7 seconds in every year. So in our daily unit of seconds, which matches with the way our pulse runs, it's a very human size unit. Okay? The age of the universe is 3 times 10 to the 17. What does that mean? It means 1,000,000 times 1,000,000 times 300,000 seconds. Huge as a number in terms of our units. Okay? Now let me give you another example of a time scale. This is another thing that most of you have not heard about. Let me first explain what it is. This symbol is the Greek letter G. It's pronounced gamma. Okay? Gamma rays is a kind of electromagnetic radiation. Now, you don't really know what electromagnetic radiation is. It is one of the things that we will learn in this course. Electromagnetic radiation is just oscillating, positive, zero, negative, changing signs, voltages, electric and magnetic effects that move as waves. Okay, so it's a wave, so it has a period. It goes up and down like that. It's something that oscillates, and that's what light is. That's what radio waves is, microwaves, X-rays, all of these different kinds of radiation and rays that we use a lot in our technology. And nature emits them. Okay, all atoms and molecules emit light, infrared, ultraviolet, okay, sometimes X-rays. All of this is the same kind of thing. The only difference is different types of situations give radiation with different oscillation periods. What is a period? It is the time for the wave to repeat itself. Okay? Just like when you are in the beach, you are playing with the wave comes, and then the next wave comes. If it's a big wave, maybe between one wave and the next wave, it will be 2 seconds. You are surfing. Okay? Now, in this gamma ray type of very, very high energy electromagnetic radiation, it is the kind of radiation that is emitted by atomic nuclei in nuclear reactions, in atomic reactors, and so on. Very high energy radiation. The period between this, top of the wave comes and then the next wave comes, that time is extremely short. Now I'll tell you how short it is. In terms of our daily unit seconds, the vibrations of atomic nuclei and the kind of radiation that they emit has such a short period. This wave passes along, if you are able to measure it, okay? One peak of the wave, and then the next peak, the time between them is 0.26 zeros and then a 1 second. Now, what we learn from this is, in science, necessarily we start from daily life units. Meter is something comparable to our bodies. Second is comparable to our bodily functions, okay? Kilogram, again, okay? I'm 86 kilograms, so it's a reasonable weight mass unit for me, for human beings in general. But nature, as we learned in the first lectures last week, has different sizes, different laws, different structures, which do not always necessarily fit to our human expectations. And as science developed and as we got to larger distances and times, astronomy, or very short distances and time scales, atomic physics, biology, molecular biology, viruses, okay, nuclei, etc., you get these very small or very large numbers. How do you cope with that? Well, one way is you always want to refer them to our own daily units. So you give them in meters, but that will require writing very large numbers. So we have to deal with a way of writing large numbers. Okay? Our common system of mathematics is based on the number 10. It's possible to make other mathematics that's based on other numbers, like 2, okay, or 3, or whatever you want. Why is the human system of mathematics, in fact, in pretty much all civilizations all over the world, based on the number 10? What is the reason for that? What is the reason?
10
We have 10 fingers. That's the human reason. But of course, abstract mathematics, treats all numbers on an equal footing. 15 is as good as 10. All right? You have to choose something. So we chose our number system as 10, and we choose our units as meters, kilograms, seconds. All of these things have to do with ourselves. But the universe, the natural world, doesn't care. This is important for our observations and our calculations. But the universe has much larger and much smaller scales. So we deal with this by finding a quick notation of writing these large numbers. You don't have to write all of these zeros all the time, 27 zeros. So you write 10 to the 27, that means there are 27 zeros. Okay? But the basic reason that we deal with very large and very small numbers is because our units refer to ourselves, but nature has its own scales, so in our units, natural scales, have a big range from very large to extremely small. So these require treatment of large and small numbers. Now sometimes, for different types of science, we use more practical units. For example, for astronomy, you have all heard of a unit called the light year. It's a large distance unit. That's for astronomical distances, which are large. A big stick, the light year, is much more convenient. But even with a light year, okay, the size of the universe is 10 billion light years. So even with a light year, it's very large. For size of a nucleus, scientists have invented a unit called the Fermi. It's 10 to the minus 15 meters. So the size of a proton is about a Fermi. Size of a nucleus is about 10 Fermi. Okay? So that makes life simpler. But not always. Sometimes, like in atomic physics, you use a different method. If you're a radio engineer, you use a different set of units, etc. But even that doesn't solve the problem. That sometimes you have to deal with very large and very small numbers. Okay? We'll do some more examples of how to calculate, how to use these large numbers, what are the conventions of writing small and large numbers, scientific notation, etc. But before doing that, I want to show you some pictures. These I just downloaded from Wikipedia. I'll show you, and then I'd like you to, I'll put them on the web, but I'd like also, you can just go on the Wikipedia and search yourselves. There is a famous saying by an ancient philosopher, a Greek philosopher, called Protagoras. This guy said, the famous saying is this: man is the measure of all things. Here man means not just one sex, it means human beings. Okay? Man is the measure of all things. This saying became almost a slogan at the times of the Renaissance, because the humanities, the importance of human beings as individuals, were very important at that time. Okay? So, of course, for all of our human civilization, culture, including science, ourselves, our bodies, our perception is the measure of all things. Everything else you compare to our bodily sizes. Okay? Now, in the saying, man is the measure of all things, there's also a value judgment. There's an ethical, philosophical thing that, we do things for our